So instantiation, as I said, is very important. You need to instantiate the array. You need to order them. The way this is typically done is by generating a static trap with an SLM or digital mirror array, DMD. And then on a polarizing beam splitter, you're superimposing some tweezers that are generated from crossed pairs of AODs. I don't think I'm telling you anything new here. And so these AODs are connected directly from the OPX. The only thing you need to add is amplifiers. The OPX outputs 4 dBm max. So to drive AODs or AOM, you need a 30 dB gain here, which we currently do not provide. But we do provide the AC signal directly, of course. And so atom array is imaged with a camera, typically. The image processing is currently performed on an image processing PC by our customers. The camera module is still in development, but it will come out quite soon. And so, yeah, the image is processed. The occupation matrix of the array is then transferred directly into the registers of the pulse processor. So you're writing directly, you can write directly from a Python API into the memory of the FPGA while the program is running. And then, yeah, the n-binary occupation matrix is transferred to the pulse processor. And currently we can transfer a 32 by 32 array in under 10 milliseconds. Of course, when we will have a tighter camera interface, it will be much shorter than that. And we will also, perform the image processing ourselves. But currently, this is how things are done in the quantum orchestration platform. So you transfer the array, and then the idea is to pick up and arrange the atoms line by line. So we are doing this a la looking, basically similar to the way it was originally done in the Misha looking group. So each atom in the row is now assigned to an oscillator, a tweezer inside the pulse processor, basically assigned to a pulse processor core. And then the tweezer frequencies and phases are set to correspond to the position of the atoms, the initial position of the atoms. And then we generate, and I will show you the details of how we do that. We dynamically generate a multi-tone chirped waveform we have the initial position of the atoms from the camera. We have the final position from a target kind of set point that we want to achieve, typically the tightly packed quadratic array, but it doesn't have to be that, it can be any shape. And so the waveform is generated on the fly for all these multi-tone chirps waveforms. So each one of the cores of the pulse processor is chirped at a different chirping rate and with a different initial and final frequencies. And so this multi-tone waveform is sent out from a single output port from the OPX and goes to the vertical or the horizontal AOD. And the other AOD is just sent a single frequency tone to set the row or the column that we're currently arranging. Now, because you have this dynamic port allocation, you can actually decide on the fly if you want to arrange rows or if you want to arrange columns. You just decide. You can look at the data on the unordered array and write some code that is running in real time in QUA on the pulse processor that decides whether it will be faster to arrange rows or columns, and you can switch in between them on the fly. That's not a problem. Yeah, so these are macros for the atom arrangement code that I will show you. So we're extensively using macros in QUA. It's hosted within Python, so you can basically use Python to write QUA code. This is very useful, so you can break your code into parts. And so these are basically the calculations that are done prior to playing the actual waveforms. Okay, so we are assigning first tweezers to atoms. So we're looking at, for a single line of atoms, we're looking at the position where we have atoms. We're deducing, we have a vector stored beforehand of the frequency corresponding to each site. And so we're setting the frequency of each pulse processor core to correspond to the frequency of each atom in this line. We're then calculating the length of the pulse because all atoms are moving together. So we're first looking for a particular line to see how far is the furthest atom from its target. So there is one atom that is the furthest from where it should be, and so that needs to traverse the largest distance. And so this one sets the pulse length because he cannot move. This atom cannot move faster than a particular. There's a maximally allowed chirp rate, maximum allowed velocity for the atoms, so as to avoid heating. And so you're taking the atom that is furthest away from where it should be, and you're dividing this detuning by the maximum chirp rate, and this is the pulse length. And then all other tweezers are moving, are playing for the same amount of time, but with a reduced chirp rate, so they're moving slower. So they all atoms start and end at the same time, but they move at different velocities. And the atom that is farthest away from where it should be moves at the fastest allowed velocity. So yeah, we're calculating the chirp rates dynamically. Then we're setting the phases and frequencies. So setting phases is very important when you're generating a multi-tone signal that goes to AOM, AODs, because you have third order interference effects inside the AOM or AOD crystal. And so you can manage to avoid this by engineering destructive interference by setting the phase of each one of these tweezers. So all the parameters of the tweezers are set, and then you're all set to play. The actual play of the arrangement pulse is quite straightforward. So just let's recap. All atoms move together with a common pulse length, but with different velocities. Yes, the pulse length is calculated by the pulse processor. The whole calculation takes something on the order of 10 microseconds. Again, because there isn't really a waveform to generate here. We're just calculating the parameters required to generate the waveform on the fly by the pulse processor, you see. And so that's why the calculation time is much shorter. And so then after we've calculated all the parameters, the tweezers are ramped up. Here it's a linear ramp. You remember this ramp construct that I've shown you before. You don't have to do this. You don't have to use a linear ramp. You can do a Blackman pulse or any other waveform that you want. And here again is an example of kind of a macro. This for loop, this 4-element index in range. This is a Python loop, and it's used to kind of generate QUA code. This play command is a QUA command. So this for loop, you can mix and match Python and QUA within a QUA program, and the compiler will simply unwrap this to be a max number of tweezer play commands. So this play command is basically duplicated 9 times by this Python macro, and every time we're addressing a different tweezer, right? From 1 to 10. Yeah, so we're ramping up all the tweezers, and then we're chirping them, right? So each one has its own chirp rate. The chirp rate is a vector now, and every tweezer chirps with a different chirp rate, and the length of the pulse is this tweezer length, tweezer moves length that we've calculated. I will show you the calculation in a moment. And so yes, this is the chirping, and this is ramping down. Basically the same thing, just with a minus sign on the ramp slope. And this is the actual code that is running, and this is the actual code that is arranging a single line in an atom array. Let's go a little bit into the details of all the calculations that are done before the actual playing. So assigning the detuning of each tweezer. This example is just here to show you that you write QUA code as you would write any high-level programming language. So you have a for loop, you're iterating over all the tweezers, and then for each tweezer, you're calculating the detuning by setting the detuning of tweezer in J2 in index J2 to be the target frequency minus the tweezer frequency. So the tweezers were already assigned to an atom. I didn't show this part. It's another for loop. And now we're calculating the detuning for each tweezer as simply being the detuning from where the atom needs to be to where he currently is. And then we have vector operations. We can calculate the maximum detuning of this tweezer vector. This tweezer detuning is a vector. And so now we know what is the maximum detuning, what is the detuning of the atom, that is the farthest away from where it needs to be. And now we're assigning a value to this length, to the tweezer moves length, which is simply the maximum detuning that we found here, divided by a maximum rate. The maximum rate is a Python variable, so you can mix and match QUA and Python variables. This is a constant. And then we're casting this to integer, also in real time, because the length needs to be, in nanoseconds, it needs to be an integer number. So we have casting also in real time. And then we're calculating the chirp rates, again, scanning over all the tweezers and calculating the chirp rate, which is simply the tuning for this particular tweezers divided by the length of the pulse. Right? And again, cast to integer because the chirp rate is also an integer. So that's it. We're really doing classical processing, nothing very fancy, but that's it. The whole atom arrangement code that you see here is like 200 lines of code or something like that, and it arranges, an n by n array. Let me show you how it looks like once we play. In blue is the actual pulse, and in pink it's the FFT of this pulse. So here you see 9 tweezers. I started them up with some random position, and now they're chirping. And you can see by the fact that you don't see any skirts here in the FFT, it means that the pulse is actually phase coherent and doesn't have any dead time, and everything runs smoothly. Well, let me run it maybe one more time. Yeah, so of course, so it's a simple piece of code to do a very important basic building block for atom arrays. Now, this is really just the first step. You need to add to that complications. You need to account for loss in efficiency in the AOM as you get closer to the edges. And moving forward, we're also working. Yes, that's the question here in the chat. Someone asked, when rearranging the tweezers, you also send modulation to vary the laser power of each tweezer. You can do that. So every tweezer, you can tune the intensity. So that's one of the complications that you typically see when you're actually writing actual code that you don't have in this example. So the amplitude can be frequency dependent, and so you can, homogenize imperfections in the RF amplifiers or in the AOM itself to have a smooth, to basically digitally pre-distort or analog pre-distort to have a smooth, a nicely linear response. Another thing that we're working on now is, and this also relates to the clock rate of an Rydberg array, is working on reservoirs. So emboldened by the fact that it's quite straightforward to make atom arrangement with the optics, with the quantum orchestration platform. We're now working on algorithms. We want to make an array and save some reservoir atoms on the edges. We already started working on code for that. And then, you run one shot of the experiment, you do your quantum circuit, you take another image, and then you, instead of redoing the pooling and arrangement from zero, you start, you just pick up several atoms from the reservoir and you fill up defects in the array. and so you can maybe win by doing that. You will be able to win on both on the clock rate and scaling to larger and larger arrays. It will be necessary to do such reservoir defect fixing to reach high probability unit occupation of large arrays. So for 1,000 atoms for a 32 by 32 array, the lifetime, the background gas collision lifetime will be such that typically a single arrangement sweep will not suffice, because after arranging for several tens of milliseconds on a large array, there will be a high probability to have one or more defects. So we will probably have to arrange larger arrays, and then in a second pass refill these defects. But so arrangement will get more and more complicated as we scale up, and doing this using DDSs and Raspberry Pis and Arduinos starts to be a pain when you want to really implement higher level sophisticated arrangement algorithms such as reservoir and so on. The third thing that you need to provide in a quantum control system for any kind of QPU, but in Rydberg as well, is coherent gate operation. So you need to be able to reset qubits, right? To do single and multi-qubit gates, to generate a universal set of gates. You might want to do adiabatic pulses, which is also a big advantage of Rydberg arrays. You have this out of the box. You can always do a simulation, use your array as a simulator, and not do gate level calculations, which is something is not so straightforward to do in superconducting qubits, for example. So these are phase coherent and precision pulses that you need to apply. So I took as an example not a quantum information processing gate per se. I wanted something a bit more general. I took a CPMG sequence as an example. I think it's a simple example that demonstrates the basic capabilities of the pulse processor. So a CPMG sequence, the standard is shown here. Here you have CPMG5. And it's basically, you start by doing a pi/2 on the x axis, and then you repeat n times delay t/2, y gate, delay t/2, and then repeat that n times, and then again close with a pi/2 pulse on the x-axis. So y-axis, performing operation on the y-axis, of course, and entails creating a phase shift of pi/2. And so the pseudocode for CPMG looks something like that. Right? Play pi/2 just to the same AOM or channel, and then repeat n times delay by t/2, phase shift by pi/2, play pi pulse now on y-axis because we did this phase shift, and then delay again by t/2, repeat this n times, and finish off with another pi/2 pulse. Right? So this pseudocode will generate a CPMG-N pulse sequence. Now, the actual QUA code running this is basically identical to the pseudocode, and this is something that is very common in QUA code. It reads like pseudocode. So how many lines of code did we have here? 7. It's 7 lines of code here as well. 1, 2, 3, 4, 5, 6, 7. You need to declare an integer. Okay, 8. Sorry for that. You need to declare the program, 9. Then you have some parameters, 2 Python variables. Okay, but it reads like pseudocode. This is the actual code that was executed. They didn't omit anything, and that generated the waveform that you see here on the right. So all these waveforms, these pi pulses, that we previously saw on this AOM1. Again, they're generated on the fly in real time. You just need to specify how long you want them to be. You can scale the amplitude. This is how we do pi over 2. We just cut the amplitude by 2. You can also do it in a different way. You can have, of course, a different waveform if you want to do some optimal control, whatever. Weighting is done here. It's in units of clock of 4 nanoseconds because the clock is 250 megahertz. So when I say 25, it's 100 nanoseconds. And so the spacing between 2 consecutive pulses is 200 nanoseconds. All right, yeah. And the frame rotation, I'm rotating by pi over 2. This takes 0 latency to do. For long pulses, also changing the frequency takes 0 latency. So, for example, and again, this is a CPMG4, right? Making this into a CPMG4 million will change nothing. It will take the same amount of time to compile, and it will just execute. This now, the time scale here now is 200 milliseconds and not 200 nanoseconds. So I multiplied everything by 1,000,000, of course. And so the pulse, the whole CPMG 4 million is now 1.2 seconds long. But it's exactly the same code that is running, that I had to do no modifications, right? Because it's not an AWG. I'm not storing anything in memory. I'm generating the waveforms on the fly in the pulse processing. If I would comment out this weight, then yes, there will be no dead time in between pulses. This is just to show you that these frame rotations are done with no latency, with no dead time. So you can see this Y pulse is being phase shifted by pi over 2 every 100 nanosecond here, and not phase shifted when we at the end. Just to scale. You can scan parameters. This now stops being a CPMG, right? I'm declaring a new variable here, calling it amplitude, sorry, calling it amplitude, and then I'm on every iteration of this CPMG, increasing amplitude to be by 1 over the number of CPMG pulses, just to create this effect. And then when I'm playing this pulse, I'm multiplying it by this amplitude scaling. So it generates these things. So you see, I didn't need to store a different waveform, a different parameter for each and every signal. So here it's a constant waveform. It's not very maybe impressive, but you can do this with a Gaussian as well. You can change the amplitude, and it will come out phase coherent just like before. If I would superimpose here another Gaussian from a different channel, they will, they will match. They will be perfectly phase coherent or not, as I wish. Yes, I can scale the duration also of the pulse. I can stretch it, as you've seen this before, right? Third order Lagrange interpolation in real time. So here I'm scaling the amplitude and the duration of the pulses, making them Gaussians, playing around basically. And it's the same code running, and everything is generated in real time. Okay, so this was a short discussion about coherent gate operations. I hope it was kind of convincing that you can generate arbitrary waveforms. There are more examples that I could show here, but then this would become really too long. Don't hesitate to schedule a one-on-one meeting with us, a private demo. Send us in the email what you would like to see. We'll prepare a demo with exactly the features that you're looking for, right? Everyone wants things that are slightly different. So this was just, to try and convince you that, you can control phase, frequencies, amplitudes, on the fly, duration of pulses, concatenate pulses, time them properly, and and so on. Another feature I forgot to mention, maybe I should have shown this, is that the phase in the numerical oscillator used inside the pulse processor is per frequency. So if you play a certain pulse at a certain frequency, then you switch to a different frequency, and then you come back to the original frequency, you will come back to the original phase. So you can, if you change the phase, you will come back to the original phase. If you change frequency and set a new phase at a different frequency, it will always come back to that phase when you come back to that frequency. So every frequency has its own phase, basically, and there is a perfect phase memory across all channels, even if you get more than one box, of course. Okay, let's talk about readout now, but not camera readout or photodiode readout. This is maybe, I wanted to talk about something that is a bit maybe less kind of appreciated as a real need among people that work with AMO systems. And so I'd like to make some kind of a mishmash between readout and stabilization and show you how we can do stabilization of parameters in real time using the quantum orchestration platform and the OPX in particular. So we have analog input channels, as you saw, and you can acquire photodiodes. You can, Seeker photon detectors if you want, and in the future also camera images. And you can use these, and all these signals that are acquired coherently, synchronously with the sequence, right? So you can effectuate a very advanced control strategy with feedback, and use that to do parameter stabilization. So if you just take a feedback loop that doesn't have a lot of propagation delay in a lab, so typical propagation delays in a lab are on the order of hundreds of nanoseconds. So let's assume this is smaller than that or negligible, and we take into account only the latencies associated with the OPX itself, with our systems. So the internal latencies are for measurement are on the order of 200 nanoseconds, plus the time that it takes to do whatever calculation it is that you want to do, right? So if you're doing, what I will show you in a moment is a PID lock loop. And so there all the calculation to calculate the proportional, the integral, the differential error, and applying all that, it takes about an additional 150 nanoseconds, something like that. So in total, so the total latency is 350 nanoseconds, and that is comparable to a lock bandwidth of more than 300 kilohertz. And this is very important. True, you can do PID lock loops with analog devices in the lab, but you cannot change typically very easily the set point of such PID loops synchronously with your sequence. You cannot decide to turn on and off the PID synchronously with the sequence. You might want to stabilize something long-term, apply a few iterations of a PID loop, and then stop and execute some circuit and then come back. The ability to do that is very important as we want to scale up processor to be large and robust. Another thing that you can very easily do in analog is if you want to stabilize the phase, for example, of a signal, you could take a bit of a reference laser, for example, and the laser that you're using to do gate operations on a fast photodiode, and in such a way use the photodiode as a demodulator, and then read out this RF signal with the OPX and extract the phase, the instantaneous phase. And this should be, you should be able to use that to, stabilize phases over long periods of time, for example, and so on. So this is complementary to optimal control. Like people are working for a long time now generating pulses that are by design robust, right? Insensitive to certain kinds of fluctuations. So first of all, there are limits, of course, to these optimal control pulses. It's an excellent thing to do, and of course we do it, and you should too. But many of these optimal control pulses, render the gate insensitive to some parameters, but sometimes more sensitive to others. There are some gates, that are rendering the sensitivity to phase noise is reduced maybe, but the sensitivity to intensity noise is increased. And so having these kind of interlaced real-time adaptive feedback loops will be able to complement these optimal control pulses and have what we call not robust gates, but adaptive gates, for which the parameters of the gates are tuned in real time based on the acquisition of some stabilizing classical signal, like photodiode intensities on photodiodes or any other signal that you can acquire with an ADC, right? Or a photon, or a single photon detector, or even a cannon. So this is an example experiment. I'm generating here a train of Gaussians, 100 nanosecond long, these Gaussians. And then I'm measuring the intensity of this with a power detector, a high bandwidth power detector. I think the bandwidth is like 100 megahertz. And then from each Gaussian to the next, I'm calculating a PID error signal on the integral, on the acquired integral of the signal, and then correcting the intensity of the Gaussian to reach a certain set point. Yeah. So as you see from the last acquired sample to the first played back sample of the subsequent Gaussian, there is about 380 nanoseconds of total latency. So that's latency inside the OPX, outside in the lab, and then back into the OPX. Right? The overall latency is about 380 nanoseconds. And then to go from that to the bandwidth of the lock, you need to divide, you need to multiply this latency by 8. This is what's typically done. Why 8? Because you need the PID loop to respond within about 45 degrees of the noise process that you're trying to eliminate, right? If you have some oscillation at 1 megahertz, it won't help you if your feedback latency is 1 microsecond, right? You won't be able to correct 1 megahertz noise with a 1 microsecond feedback latency. You need at least 125 nanoseconds of feedback latency to reach 1 megahertz feedback, so that you can correct in all the linear regions of the error process within 45 degrees, basically, to have a stable lock. So anyway, I'm repeating this strain of Gaussians. And here you see how the PID is stabilizing to some set point within four shots or so. So within a microsecond or so, it stabilizes. And this can be used for slow locking. And this is the actual PID code. This is the actual QUA PID code that is running to generate the data that you saw before and that you will see in the future. It's 15 lines of code. That's all, and 5 lines of Python for the parameters, for the target set points and the PID coefficients, and the alpha to define the memory for the integrator. There are just a declaration of variables, a fixed and integer, and then there is a for loop that is the actual PID loop. I'm running this 10,000 times. It can be run indefinitely, it can be an infinite loop. And then what I'm doing, I'm measuring this Gaussian, I'm sending this Gaussian pulse scaled by this amplitude to a laser. And then I'm waiting some time of flight and then opening an integration window and doing this integration full, basically calculating the integral of the envelope of the pulse that I acquired with the photodetector, and saving the result of this integral into this QUA variable called integ. And then I'm calculating the error, which is simply the distance of this integ from the target. I'm doing some bit shift here to have a better dynamic range because the signal is small. So this is very efficient, and to bit flip, to bit shift to multiply or divide by a power of 2. I'm calculating the integrator as being simply 1 minus alpha times the integrator error plus alpha times the error. This creates an exponentially decreasing integrator error with a memory coefficient alpha. It's typical. This is a typical way to implement integrators in numerical PID loops. Calculating the derivative, the assign command is the equal sign. which is simply the old error minus the new error, assigning the old error to be, sorry, the error. And here I'm assigning the amplitude here, which is simply the old amplitude plus the PID expression here, the gain times the error plus the integrator gain times the integrator error plus the derivative gain times the derivative error. Yeah, so it's really reads like PID pseudocode, right, that you would learn in any classical control, course. But this thing runs at 300 kilohertz. Right? You're writing this in a language that resembles Python. You're writing 20 lines of code, but you're executing this at 300 kilohertz. Okay, understand? I hope I'm conveying the message of how powerful this is. You could get these performances, but not by yourself on programming your own FPGA. But you won't get these performances, and you will get the same performances, not more. But you can't get them anywhere else by writing so little code, which is so straightforward and intuitive. So just to stress test this, so I'm introducing now 50 kilohertz of noise on my signal, on my Gaussian train. And here where it says lock starts is where I'm turning on this PID and I'm reducing the 50 kilohertz noise. And this is where the noise stops, this jump. And so just to show that I'm limited by the detection noise flow, which wasn't great, but 50 kilohertz is well within the bandwidth of the PID. So now since this PID is running in real time on the pulse processor, also the parameters of the PID, so all the gains of the proportional and integral and differential, this alpha could in principle also be QUA parameters, the QUA variables. And so the whole, you could make a meta optimization of the lock parameters also in real time, right? And so converge and make very robust locks. 200 kilohertz noise is not fully cancelled, so the bandwidth is 300 kilohertz or so, or maybe a bit more, but it's a 3 dB point. Right? So at 200 kilohertz, I'm reducing the amplitude by a factor of 3, which is compared to reducing the power spectral density noise component by about 10 dB, right? The actual power of this noise is reduced by 10 dB at 200 kilohertz. Right? This is not really negligible. And this is a simple PID loop. This is just a demo here that I'm showing. We've done things which are much more complicated than this. We've implemented Bayesian estimators that run in real time, and improve sensitivity to measurements, and to use optimal use of measurements. You can implement Kalman filters, machine learning based methods. You can do anything that you can write in Python, you can in principle write in QUA, right? And then it will run with this kind of bandwidths. So it's really, we think it's a paradigm shift in the way that you design and control sequences. And everything, of course, from a high-level programming language that you should have shown. So this is the last slide I have. So it's just a conclusion on this PID thing that is often not really appreciated in AMO. There is this kind of legacy idea that since we've always managed to walk around with our 1 microsecond time step sequencers, and since the cycle time is hundreds of milliseconds, we could in principle always update the waveforms shot to shot via some PC and throw them out via some DAC ourselves. But we are losing a lot by doing that. The feedback that you can do with a system such as ours is not something that is simply nice to have. This will directly improve the gate fidelities of your circuits. Right? The ability to mitigate laser intensity fluctuations will directly improve the gate fidelities of your processor. And this is something that you cannot really do by doing things offline, as many are doing today, loading a waveform to some kind of AWG-like system and then triggering it to output. And so, and as circuits will become deeper, as we will want to start doing, tens, maybe hundreds of gates, then intra-circuit stabilization will become important, right? Fluctuation, acoustic fluctuations, vibration, noise on the laser, will start to be, is already, a limiting factor. And as circuits will become deeper, there will be a need to make this kind of intra-circuit stabilization. Shot-to-shot fluctuations, of course, are also within the loop. It's not an issue. And then the limits of this bandwidth. So you would also want to do maybe intra-gate, calibration, and you can do that, by the way, with the simulator pulses. So pulses which are tens of microseconds or 10 microseconds long, where you cause some, arbitrary frequency chirp, frequency modulation, and amplitude modulation. Since the pulse is long enough, it's several, it's 10 microseconds, so you can break it into parts. I've shown you that you can glue different parts, with zero latency, with zero dead time. So you can break it into parts and have like an interleaved PID loop that is optimizing the pulse as it's being played, right? To make an optimal, adaptive optimal control pulse for simulators. You can do that in ions for the normal gates, because the ion arrays, ion trap computers, the typical pulse lengths are in the hundreds of microseconds. In Rydberg arrays to do feedback on a 100 or 50 nanosecond time scale, it's not us limiting you, it's the propagation delay through the AOM itself, right? This will always be on the order of several hundred nanoseconds typically. And so you won't be able to respond, fast enough to adapt a gate in real time. But gate to gate is doable, and we've demonstrated that. Yeah. So that's it. This is my last slide. So I think I've shown you a taste. I didn't show you the full set of capabilities. That would take longer, and it's better to do that one-on-one. Just contact us, send us a short email telling us what exactly you're trying to do, and we'll prepare a demo, focusing on your needs. We do that all the time. We can also give you access to a simulated environment of our pulse processor so that you can play around. There are many other features I didn't discuss, and I could, each word here could be a separate presentation, but I hope I gave you like a feeling of some sense of confidence that you can perform all the basic control needs required in a Rydberg-based, neutral atom-based quantum processor. So preparing the qubit reservoirs, laser cooling and tapping, doing arrangement of atom arrays, even large ones, doing coherent gate operations, readout, and stabilization and characterization of all the associated parameters. So if there are any questions, this will be a great time to ask. Otherwise, we can stop here also.
I have a question. Can
yeah.
I? So you didn't mention, maybe I missed, but like if you're using the readout of a camera, then you can use like the Python libraries to image treat and turn this into feedback for these for your operation, or how do you do that?
Yes. So currently the way it's done is that you take an image, you have a PC in the lab that does the image processing. You connect it to the camera via USB or camera link. You take a picture, you do the image processing in the PC, and then the PC transfers to the pulse processor already the array, the occupation matrix. So a Boolean matrix with zeros and ones where there are atoms, right? And then the pulse processor takes this matrix of ones and zeros and constructs the arrangement waveforms from that, right?
Okay, thank you.
Yeah, and in the future we will introduce really a camera interface module, which will do the image processing internally, and we're really hoping to be able to shave off several milliseconds of the communication you know, the frame grabbing process from the camera to the PC and so on. And you know, and the objective is really to, at least for regions of the array, to be able to do that in, you know, microseconds, so that it's you know, relevant for quantum error correction.
Okay, thanks.
No problem.